So this is lesson 3.6 on multiplying matrices, and we've talked about adding matrices already. So if you haven't watched that video, it is really important that you watch the video on adding matrices. Adding matrices and multiplying matrices take on two entirely different fields. When you multiply matrices, we now have to incorporate multiplying a row by a column and adding the results. And so multiplying matrices gets much more challenging than simply adding the corresponding entries in those matrices or subtracting them when you're doing adding and subtracting. All right? So first of all, in order to multiply matrices, we have to have, if I had matrix A times matrix B, effectively what we have is if I want to multiply a M by N matrix, and I want to multiply that by P by Q matrix, for example, the only way to multiply those two is if these two numbers right here match. Now, the best way to do that then is, remember, this is rows by columns, and this is rows, and this is columns. So the definition and the way this is going to say it in the book is it's going to say that the columns of the first have to match the rows of the second. So long as these two quantities, again, the columns of the first matrix and the rows of the second matrix, as long as those two match, you can multiply these two matrices together. And for the record, the result then is going to be M by Q. All right, so let's take a look at a couple of examples here. All right, we want to multiply matrix A by matrix B. And so matrix A by matrix B, it says because the number of columns in A, which is 3 columns, again, 3 columns here, does not match the number of rows in column B, which is 4, then the product of B of AB is undefined, is not defined. All right? Now, again, the way that I would do that is I would simply look at, instead of going through all of this business, I would simply look at this number and say, do these two numbers match? Since they don't, this is not defined because those don't match. Here, we want a 3 by 3 times a 3 by 2. Since the columns of the first match the rows of the second, these are both the same number, that means that this is a defined product, and the result then will be these n numbers, a 3 by 2 matrix. All right? So again, as long as these two numbers match, the result is the bookends. All right? Now, to find the element in the, now I don't know why they chose I and J, but the ith row in the jth column, I don't know why they chose I and J. They could have used A and B, but they didn't want to because of this A and B, so they didn't want to get things confusing. So they chose I and J, and I don't know why. But what we're saying here then is to find the element in the ith row J column of the product of matrix AB, each element in the ith row of A, we're going to be multiplying each each element in the ith row of A by the corresponding element in the jth column of B. All right? And then add the products. Now, in words, that makes absolutely no sense. True? So, we want to multiply the first row by the first column. And that is going to give us the result in the first row, first column. So we will then multiply the corresponding entry, A times E, plus B times G. And so that's where we get this entry, AE plus BG. All right? Let's try a different color of that and see if you can follow along with me. To find this entry, which would be the first row, okay, first row, second column, we're going to multiply the first row, which is A and B. We're going to multiply A times F plus B times H. So A times F plus B times H. And so there's where you get AF plus BH. Now listen, this is not something that's very easy to talk about when you're using variables, so let's get right into a real example and let's see if we can make some sense of this thing. First of all, we need to determine, is this product possible? You're multiplying a 2 by 2 by a 2 by 2. And so since those numbers match, the result is going to be a 2 by 2 matrix. All right? Because A is a 2 by 2 and B is a 2 by 2, the product of AB is defined, and the product is a 2 by 2 matrix. Now, if I want to find the, again, you kind of have to look at this. Maybe I have some success doing it this way. I'm going to break this lower matrix up. Okay, this is our product of AB, and by putting the crosshairs in there, hopefully they'll let you see that this right here is the first row, first column. All right, this right here would be the first row, second column entry, and then we can simplify this stuff as we go. All right. So if I want to multiply first row, first column, all right, so I want to multiply the first row by the first column, all right, first row by the first column, and then add the results. So this becomes 1, oops, I want to pick a different color pen, that's probably hard to read, 1 times 3, so there's 1 times 3, plus negative 2 times 7. Negative 2 times 7. Again, we're multiplying row by column. Now, when we go to simplify that, this is 1 times 3 plus negative 2 times 7. This is negative 14. This is positive 3. So positive 3 and negative 14 is negative 11. All right? Okay, so now I'm going to clear this off. And you guys, unfortunately, don't have the opportunity to wipe this stuff out of here. So you're going to have to kind of do your best at following along. When I look back at the second row, second column, I think I use, or sorry, first row, second column, I think I use this blue here. I want to go first row by second column. All right, so again, first row by second column. And so this ends up being 1 times negative 6, 1 times negative 6, and then negative 2 times negative 1. Now do some simplifying. 1 times negative 6 is negative 6. Negative 2 times negative 1 is positive 2. Negative 6 plus 2 is negative 4. Okay. Once again, I'm going to do some erasing here. And let's go back and take a look again. Now what I want to do is I want to go, let me pick a different color again. Let's go with purple here. All right, so now to get the second row, first column, again, the second row, first column, that's this down here, I'm going to go second row by first column. And so this becomes 5 times 3 and negative 4 times 7. And then 5 times 3 is 15. Negative 4 times 7 is negative 28. 15 minus 28 becomes negative 13. And then finally, for our last one, we want row 2 by column 2. So 5 times negative 6 and negative 4 times negative 1. 5 times negative 6 is negative 30. Negative 4 times negative 1 is positive 4. And so this is negative 26. Now, that's an awful lot of work to do. But again, it's necessary and relevant, and so to multiply matrices, again, you multiply row by column, and so that's going to give us the first row, first column entry right here. All right, whatever that happens to be. All right, so let's give one a shot. I know this is going to seem a little overwhelming at first, but let's go ahead and give one a shot. Try these 2 examples, and then we'll go ahead and restart your video and check it out, okay? All right, so for A, this is 3 rows by 2 columns. So this is a 3 by 2 matrix. This is 2 rows by 2 columns, and so that's a 2 by 2 matrix. And so the result then, since those 2 match, we can perform the multiplication. The result is going to be a 3 by 2. Now, to find the product of 6, 2, negative 1, 3, 0, negative 4 times negative 1, 2, 5, and negative 2 equals. We're going to be doing a little bit of mental calculation here, so if we go too fast for it, certainly you're well within your rights to use your calculator as you need to. But if I want to find the entry, and again, I know I'm going to have 3 rows, 1, 2, 3, and 2 columns here. So I should end up with 3 rows and 2 columns. And so maybe perhaps I might want to take this thing and move it up just a little bit. Might have a hard time fitting everything in there. There we go. Now I should be able to get 1, 2, 3 rows in there. All right. To get that, then we're going to go first row by first column. All right. And so again, because the rows and columns matched, we know we're going to have the same number. 6 times -1 is -6. 2 times 5 is 10. So -6 plus 10 becomes +4. And so my first entry is +4. Okay, now I'm going to do first row times second column, and that gets me this entry here. So 6 times 2, 2 times -2. 6 times 2 is 12. 2 times -2 is -4. 12 take away 4 is in fact 8. And so there's our entry there. All right. Now we have the first row done. We're going to go ahead and cross off the first row here, and now we're going to go second row by first column. -3 times -1 is 1. 3 times 5 is 15, so 1 plus 15 is 16. Now we've got that done. We're going to go -1 by 2. 3 times -2, so that's -2, -6, that becomes -8. And then we're done with this row. Now we're going to do row 3. Row 3 times column 1 becomes 0 times -1, -4 times 5, which is -20. And finally, 0 times 2 is 0, -4 times -2 is +8. And so our matrix is 4, 8, 16, -8, -20, and +8. All right, so in this example then, A is a 2 by 2. And again, B is 2 rows by 1 column, so this is 2 by 1. Since these two match, that's okay. The result is going to be a 2 by 1 matrix, so my result needs to have 2 rows, 1 column. Okay? So we'll go ahead and we will multiply then row 1 times column 1. And so row 1 times column 1 becomes 4 times 9, which is 36. -2 times 12, -6 times 2 is -12, and so 36 take away 12 becomes 24. In the second row, it's a little bit more challenging math because we're getting into a little bit bigger numbers here, but 7 times 9 is 63, and then 3 times 6 is, 3 times 2 is 6, and since they're both positive, it's just a plus sign, and so this ends up being 69. And so it's 2469 is your result. So if you did that and you got that right, congratulations, you're well on your way to doing this particular lesson. All right, so now we're just going to give you a series of, we give you a bunch of 2 by 2s, and so if they're all the same, we've got 2 2 by 2s, and we have 1 2 by 3. And so let's see if these things are even defined first. We're doing A plus B, so can I add 2 matrices that have the same dimensions? Absolutely. And then the result would then be a 2 by 2. And I want to multiply that by C, which is a 2 by 3. Since those match, the result is defined, and it's a 2 by 3 matrix. All right. For the second example, we want A times C. Well, once again, that is a 2 by 2 times a 2 by 3. And so the result will be a 2 by 3, and the same is true for B times C, and then we can add them together because they're the same dimensions. All right, so let's go ahead and run through this. Again, we're going to first add A and B. We might as well go ahead and add those two together first if we can. So when I go to add these 2 matrices together, I'm going to go ahead and do 4 and 1, and 4 plus 1. Again, we're adding, so 4 plus 1 is 5. -3 plus 7 is 4. -1 and -4 is -5, and 2 and -2 is 0. So now when we go to multiply, we're going to do row 1 by column 1. 5 times 3 is 15, 4 times 1 is 4, and so that becomes 19. When I go to do row 1 by column 2, this is 5 times -5, which is -25, and then 4 times 0 is simply 0, so it's -25. 5 times 4, so 5 times -2 is -10. 4 times 6 is 24. -10 and +24 is 14. taking a look at the second one now that we've taken care of that, now we're going to be doing negative, can't remember, yes, this was negative 5, sorry, I kind of written over that. So now this is negative 5 times 3, which is negative 15, and then 0 times 1 is just 0, so this is just negative 15. Negative 5 times negative 5 becomes positive 25, and then 0 times 0 is still just 0. And negative 5 times negative 2 is positive 10. And again, when I do the 0 times 6, you're just going to get 0, so you're not adding anything to it. Sorry, this end got a little messy. Let's see if we can clear that up for you. This was 14 and 10. There we go. All right, so now if we want to do AC times BC, we have to first take the product of A times C, then do the product of B times C, and then add the two results together. So as I go ahead and perform this matrix multiplication, again, we're going to do 4 times 3, which is 12, minus 3, which is 9. And this may take a little bit of space. But I'm going to go ahead and perform the multiplication. 4 times negative 5, negative 3 times 0 is negative 20. 4 times negative 2 is negative 8. 3 times negative 6 is negative 18. And so that's a grand total of negative 26. On the second row, negative 1 times 3 is negative 3. 2 times 1 is 2, so that becomes negative 1. Negative 1 times negative 5 is positive 5. 2 times 0 is 0, so this is positive 5. And finally, negative 1 times negative 2 is positive 2. And 2 times 6 is 12. And so when I add 2 and 12, I get 14. So there's the first multiplication. Now I need to do that again. Now I'm going to do B times C. So now I have to do this times this times this, etc., etc. I'm going to save you the trouble of this. I'm going to go ahead and write the solution in, but you can verify this for me, and I will show you a much easier way to verify for me much later in class. Whoops, sorry, that's not correct. This should be negative 10, negative 5, 40. This should be negative 14, this should be 20, and this should be negative 4. Now, when I go to add these two together, I simply add entries. So 9 and 10 makes 19. Negative 20 and negative 5 is negative 25. Negative 26 and positive 40 becomes positive 14. Negative 1 and negative 14 becomes negative 15. 5 and 20 is 25. And finally, 14 minus 4 is 10, and so there's my result. Those are quite lengthy problems. Not hard, just tedious, I think, is probably the best way to describe it. All right, some properties of matrix multiplication. The associative property of multiplication is so long as AB and CB matrices such that they're all the same dimensions, the dimensions have to match for this to work. Or the dimensions have to be such that, again, the rows of this one match the columns of this one, or vice versa. Columns of this match the rows of this, etc. But anyway, the associative property of matrices is very similar to the associative property of, like, multiplication. Just like normal, like 2 times 3 times 4. If I do 2 times 3 first and then do 3 times 4 first, either way I should get 24 in both cases. So that's true for matrices. The left distributive property, notice we call it the left distributive property because actually you'll see in here there is no commutative property. It is not true that A times B is equal to B times A. This is not the case. Now that's true if you're just doing regular old numbers, because for integers or for any real numbers, products of those should be commutative. But that is not true for matrix multiplication, and the reason for that is if you think about it, suppose A was a 2 by 2 and suppose B was a 2 by 3. Is that product defined? Well, certainly, because 2 and 2 match, the result would be a 2 by 3 matrix. But if B is a 2 by 3 matrix and A is a 2 by 2 matrix, if I tried to do B times A, now 2 and 3 don't match. And so now I can't do that multiplication. That multiplication does not even exist. So there is no commutativity for matrix multiplication. So we have to have two different distributive properties because it's not commutative. You can't switch the order. So effectively this is A times B plus A times C. If it's right distributive property, it's the same idea, but it's A times C plus B times C, leaving the C on the right. Finally, the associative property of scalar multiplication. This is a little bit tricky, but effectively what you have is you have that this is you can do k times a, so you could do the scalar times the matrix A and then multiply by b, or you could do a times the scalar times b. You don't multiply the scalar by both of these. This isn't a distributive property problem. Instead, you can either do the scalar by a and then times b, or the scalar by b and then times a. But you don't have to do the scalar times both of them. It's just by one. Whoops. So, the school stores from middle school and high schools each submit an inventory list for the year. Each sweatshirt costs $15, t-shirt costs $9, and each pennant costs $5. Use the matrix multiplication to find the total cost of the inventory for each school store. So for the middle school, they have 61 sweatshirts. 61 sweatshirts. They have 63 t-shirts and 74 pennants. And for the high school, they have 58 sweatshirts, 71 t-shirts, and 92 pennants. All right? And it says and then we know that the cost of a sweatshirt is $15. We know that the cost of a t-shirt is $9, and we know the cost of a pennant is $5. So if I was trying to find the total amount of money that the middle school had invested into material, I would have to do 61 times 15, because 61 sweatshirts times $15 a sweatshirt is going to give me the total amount of money they have wrapped up in inventory in sweatshirts. And then 63 times the number of t-shirts, and then times the cost of a t-shirt, and then 74 times the cost of a pennant. And then add all that together, and that's going to give me the inventory cost for the middle school. Now again, this is a 2-row by 3-column. This is a 3-row by 1 column. So since these dimensions match, we can perform the multiplication. The result is a 2 by 1 matrix. And again, that 2 by 1 matrix is going to be the total amount of money for the middle school and the high school. So when I go ahead and do this multiplication, what I'm looking at now is I'm going to be doing 61 times 15 plus 63 times 9 plus 74 times 5. And again, 61 times 15 is that, 63 times 9 is that, and 74 times 5 is that. So we've done first row by first column because there is only one column. And again, we're adding those results together. Now, for the high school, 58 times $15 a shirt, so 58 times 15 plus 71 times 9 plus 92 times 5. And now we just have to add, we have to multiply and then add, and so altogether you're going to end up with this result matrix. When I do 61 times 15 plus 63 times 9 plus 74 times 5, altogether that is 1852, and for the second line this is 1969. And so as a matrix, the total cost in dollars is 1852 and 1969. So the high school has $1,969 wrapped up in inventory, and the middle school has $1,852 wrapped up in their inventory. All right. The final page then of the lesson is a couple of checkpoint problems. I want you to go ahead and try these, and we'll go ahead and look at the solutions of them in just a moment here. All right, so first we want A times BC. First of all, we have to determine if B times C is even possible. This is a 2 by 2, and this is also a 2 by 1, sorry. That's a 2 by 1. And so the result of B times C is going to be a 2 by 1 matrix. Matrix A is 3 by 2. And so since these two match, the result of this whole thing is going to be a 3 by 1, 3 rows by 1 column matrix. Again, it's those bookend numbers that helps us to determine our dimensions. So first we have to do -2, 3, 0, 1, -2, and 4. And we're going to multiply that by the product of B times C. Now, B times C becomes this row times this column. So -2 times -3 is 6. -4 times +2 is -8. +6 minus 8 becomes -2. When I do row 2, this is 5 times -3, which is -15, and then 1 times 2 is 2, so this is -13. Now we have to do row 1 by column 1, And so 2 times negative 2 and 1 times negative 13. 2 times negative 2 is negative 4, and then 1 times negative 13 is negative 13. Negative 4 and negative 13 all together should come out, excuse me, this was negative 2. This is negative 2 times negative 2 becomes positive 4, and then 1 times negative 13 is negative 13. In any case, 4 minus 13 is negative 9. 3 negative 2 times negative 2, negative 13. 3 times negative 2 is negative 6. Negative 2 times negative 13 is positive 26, and so this becomes positive 20. And finally, 0 times negative 2 is 0, and then 4 times negative 13, well, 4 times negative 13 is negative 52, and then since that's 0, this is this negative 52. And so that would be the result of that product. And finally, now we're going to take a look at that t-shirt example again, that school store. It says, suppose the sweatshirt costs $17, the t-shirt's $11, and the pennants are $7. Calculate the total cost inventory for each school store. So again, now what we would do is we would take our cost matrix, would be 17, 11, and 7, and we would go back to that original matrix, what we started with on the previous page, which was 61, 63, 74, 58, 71, and 92. And I'm not going to go through all the math on that, but effectively we multiply this row by this column and add the results. And you should get a total inventory of 2248 for the middle school. And then for the high school, we do each entry there times each entry there, and that gives us the total inventory, which is 2411. So that says the middle school has roughly $22,048 in inventory, and the high school has $24,048.